Well, we're here at the end of the semester, just about. Got what, about 2 more weeks of class? So while I was out, I gave you guys some extra videos to watch about rotational inertia. I see that you've completed the homeworks on that. Everybody seems to be doing fine on the homework. A few notes before I get started here. Number one, I understand that a lot of you were impacted by the tornado a couple weeks ago. And some of you may have been without power and internet for quite a while. I am aware of that, and I will be considering that as I go to grade this next couple of assignments, our last test and your final grade. Having said that, though, I don't foresee any problems. Most of you guys are doing just fine with the class. Just keep it going. We got a couple more weeks and we'll be done with this. My intent is to cover probably this chapter on fluids, and I think the next thing I cover will probably be oscillations and waves, and give you a little bit of overview of that. And then we'll go into our final test. I'll give the final test on the last day of class in here. And I think what I'm going to do with that is make it a little bit longer test, since really you're going to have a finals week, and since I don't typically give a final, and there's been a few things that we've covered up to this point, I think what I will do is make it a little bit longer test, but give you a little bit longer time to complete it. So expect something very similar to the format of the last test, where you'll have a few things that come from the homework, and you'll have a few questions that I will expect you to do some work, scan the thing, send it to me, and I'll take a look at your work from there, so that we can cover everything that we need to cover that I think is important from this chapter. Also, as always, if you start struggling, if you need help, feel free to reach out to me. I know a lot of you have already, particularly concerning the issues we've had with the weather and power outages and things. So that's all fine. Everything's gonna be okay. So let's get into the next piece of this. This is our fluid statics. So you have heard terms before where we talk about statics and dynamics. In the last couple of chapters, we introduced the idea of static equilibrium and dynamic equilibrium. And remember, with the things that we were doing with equilibrium, tended to be things like looking at collisions and how momentum is conserved. We looked at torque, which is really just an equilibrium problem, right? It's just the different, like the seesaw problems and the ladder problem, that kind of thing. So the same sort of thing is going to happen here, except we're going to look at this from the standpoint of a fluid, as opposed to just some solid static system. These notes, by the way, are up on Blackboard for you. So we need to define what a fluid is. It's not really as easy as you might think. Generally, we think about matter as existing in the solid, liquid, or gas phase, plasma as well. And generally, you talk about fluids and you think about a liquid, water, for example. Great example of a fluid. The actual definition of fluid is far more complex. But for the case of what we're going to talk about with this, you can think of fluids in the same way that you think of liquids, things that flow. They have low internal friction. They assume the shape of their container, this sort of thing. So nothing really overly complicated. If you really care about getting into the definition of fluids and solids, then take some graduate level courses in fluid dynamics and solid state physics, that sort of thing. So here's just kind of in this slide as an example of what we're talking about. So in example A here, this rock or whatever it is, what we're looking at is kind of the molecular structure of this rock. And these little red dots represent atoms. So let's say that this is a brick of iron, whatever that looks like. Each of those red dots represent an iron molecule. And we notice that in the solid, you could, if you drew this as a system that we've been dealing with the last couple of weeks, you notice that you can have some vectors here and you can look at the forces between all the different iron molecules. You could almost model this, if you wanted to, as a spring connecting these masses. And we'll talk about springs and oscillations a little more next week. That generally is how we think of solids, something that has a very rigidly defined structure. Perhaps the things oscillate as if connected by a spring between each other, but they still kind of maintain the same shape. Fluid is more like example B here. So this is your liquid where you have some fluid, let's say this is water. And each of these dots represents a molecule of that substance. So water obviously is 2 hydrogens and an oxygen together. So each of those dots might represent that combination of an oxygen molecule and 2 hydrogens. But notice that there is no kind of solid structure. You can't really build a square or cube or diamond or something out of this. You just kind of have these individually flowing things, but they're still relatively close to each other. They can pass by each other, but they can cause some resistance, this kind of thing. Well, if you take those and you spread them out even further, notice that they typically don't interact with each other as much. They tend to move around. There's a lot of space. This is our gas. Gases and liquids can both behave as fluids. So when we talk about a fluid, generally that's what we mean is we're talking about either a liquid or a gas, generally not solids, and generally not plasmas, which is example E there. Notice plasma looks a whole lot like a gas, except in addition to the little red element dots, we have these little blue things that represent free electrons. And the reason that we typically don't measure plasma as a typical fluid or gas is because of these free electrons. They cause significant interactions between particles because of electrostatic forces that you learn about in physics 2. But because we don't want to account for those in this class, we're just going to kind of ignore the plasma state of matter because it does get very, very complicated. So what we're talking about here is fluid statics. So we're going to talk about this idea of either a liquid or a gas, just some fluid, and how it behaves effectively at rest without moving through tubes or something like that. And we're going to see some examples of that here. Reset. So one of the things that a concept that we need to understand when dealing with fluids is this concept of density. So what does density mean? Density is a measure of mass per unit volume or area, depending on which one you want, right? Let's talk in terms of mass per unit volume in general. So think of a three-dimensional cube and the amount of stuff that's in that cube. The more tightly packed that is, the higher density it's going to have. So in this example, we have effectively a balance problem, right? This is a seesaw problem from the torque examples. And on one side of the balance, we have this giant stack of bricks. On the other side, we have a giant pile of feathers or hay or something. Now, obviously, if you take a brick, that's going to weigh way more than a feather or a straw of hay. So this is an important difference. This is an important distinction. When we were doing this as a torque problem, remember, it's about forces. Forces are just mass times acceleration, right? In this case, the force that we were typically worried about was the weight. So we needed the mass, the amount of stuff in an object, times the acceleration due to gravity on the thing to get our weight. This implies, this diagram, if this system is in equilibrium, if it's balanced, that means we have the same amount of weight on each side of the balance. Or at least the torques are equal, right? The weights don't have to be equal, remember? We could have a completely different weight on one side, but remember, we have to move the rotational arm. We have to move that arm for our inertia. In this diagram, we're going to assume that these two masses are equidistant from the pivot. So if this happens, if they're equidistant, I mean, they have to have the same weight. And we can notice that very easily. It takes a whole lot more feathers to make the same weight as the stack of bricks. This is because the density of the feather is much, much lower. There's less stuff, right? So in fluids, we need to be concerned about density a lot of times. So remember, the way we calculate our density is mass per unit volume. So typically you'll see something like mass is in kilograms, volume might be in cubic meters. So you might be kilograms per cubic meters, something like that, right? So that's your density. So density is going to relate to force. Think about this. If density is mass per unit volume, then since mass and force have a relationship, then we must be able to come up with some sort of equivalent of force. And the equivalent of force that we're talking about here is our pressure. Pressure is force per unit area. The place that you have heard of pressure before is typically when you go out to put air in your tires. You might have your owner's manual might recommend 32 psi for your tire pressure. That's pounds per square inch. Think about what that means. Pressure is 32 psi, pounds per square inch. So that means you have pounds, which is a measure of weight, which in and of itself is a measure of force. And then per, so on the bottom of the fraction, you have square inches or inches squared. Or you might have cubic inches, right? Typically, our air pressures are pounds per square inch. So our pressure is force per unit area. Since area is the square of a distance, that's where you get the square inches, right? So if you look at this diagram, what we've got is somebody on the left side here takes their finger and they poke you in the shoulder. And let's say that we don't apply a whole lot of force, just kind of gentle poke. The area, surface area of that person's fingertip is going to be relatively large compared to, let's say, a needle. You're getting a shot. So if we take a needle, though, and we apply the same amount of force, just that gentle push with a finger, but now we apply the same amount of force, but instead of using the big fat surface area of your fingertip, you use this very, very tiny surface area of the tip of the needle. You're going to feel that. The harder you push, the more you're going to feel that. So I want to show you something on the board here. Pen. So you've probably all seen things on the news where somebody went crazy on an airplane and they tried to open the emergency exit door in flight. And you've probably seen movies where a guy does this and everybody gets sucked out. That doesn't happen at all. So I'm going to show you an example of that. So first of all, I'm going to write down these couple of equations. Remember, density is mass per unit volume. We use the Greek letter rho. It looks like this kind of script P. So this is what we use for density. So density is mass per unit volume. Typically mass is in kilograms and volume is cubic meters. The other thing that we're looking at is pressure. Pressure is force per unit area. Remember, our force is in newtons. Area is typically in square meters. So your density and your pressure. This is one of those weird things in physics where we use a symbol that's really, really similar, right? We have rho for density and we have capital P for pressure, but remember we're using P for momentum. But we were using lowercase p for momentum. So it's one of those weird things in physics that you just kind of have to get used to, and you have to understand context of what we're doing. So let's take a look at the airplane door. Now, typically, the way airplanes work, let's see if I can draw an airplane. So typically the way airplanes work is we're flying along Fat, Dumb, and Happy, or at least 2 out of the 3, at some altitude. Now you may or may not know that the higher you go in altitude, the lower the pressure. So let's take a look at that real quick. So here's our pressure. Pressure is a function of force per unit area. So let's imagine that we have an aircraft that sits on the ground on a runway somewhere, let's say Little Rock. I happen to know the field elevation at Little Rock is about 500 feet above sea level, roughly. And we're going to talk about that in a second. But we have some baseline. Now, as we increase altitude, the volume contained inside this aircraft does not change. So we can't do anything about that. But what's going to happen as we increase our altitude, what happens is our density is going to decrease, the density of the air. There's less air at higher altitudes. So our density decreases. Well, if our density decreases, then volume of the atmosphere is not going to change if we stay consistent. But the mass, the amount of stuff in that volume is going to change. So if our mass decreases and the acceleration of gravity on that gas does not change, then that means our force must decrease as well. Since our force decreases, then our pressure must decrease. So typically at sea level, our sea level pressure, SLP, is 14.7 pounds per square inch. That's just normal atmospheric pressure. So what that means is that if you took a column of air and it was 1 square inch in area and then infinitely tall up to the edge of space, the amount of air in that cubical column would weigh 14.7 pounds. Now, as we increase in altitude and there's less stuff, then our pressure at altitude is much, much lower. At 30,000 feet, for example, the pressure outside the aircraft might be on the order of 5 or 6 psi. So we're getting down to pretty low pressures. Incidentally, this is why if you're on an airplane and they tell you during the safety brief that if we lose pressure, that this mask is dropped down, and then once you put it on your face and scream into it while you die. This is not to provide oxygen. There is still the same amount of oxygen at higher altitudes. There's just less pressure. And your lungs, your body is designed to operate at 14.7 psi. It's no longer 14.7 psi. So you need to be able to force the air into your lungs, and that's what that little cup does. So anyway, let's say that outside the aircraft, the pressure is very, very low, down at 5 psi or something. I don't want the inside of the aircraft to be at 5 psi because everybody dies, or they have to wear the mask, right? You're going to pass out. So what do? We pressurize the airplane. This is why you can feel your ears kind of getting weird as you increase and decrease altitudes, because of pressure change. So we have to pump air into the aircraft. So ultimately what happens is the inside of the aircraft might be at something like, typically it's about 10 or 12 psi. It's a little bit lower than actual sea level pressure. But outside the aircraft might be down to like 6. So that means we have what's called a differential pressure, PSID. So our differential pressure inside the aircraft might be 5 psi. And because it wants to be in equilibrium, it's 5 psi that's inside the aircraft pushing everything out. On the ground, you don't have the pressurization system on, so the pressure inside the aircraft and the pressure outside the aircraft are equal, thus your PSID is 0. So why do we care? So let's take our typical emergency exit door. The first thing to notice about emergency exit doors is they always open to the inside. Next time you go flying, take a look at that. If you sit in the exit row, the instructions are to unlatch the door and then you pull it inside the cabin. So let's find out what's going on. If you were to unlatch that on the ground, that door is just going to fall out. And that door weighs a little bit, but it's not much. It weighs much, much less than you think. The door itself probably weighs 20 pounds. But what's happening in flight? Let's think about how big the door is. So the door is probably, I'm just going to estimate about 4 feet by 3 feet. So we convert this to inches because we need a pressure in inches. So 4 feet, that's about 48 inches. And 3 feet is about 36 inches. So the area of this thing is 36 times 48, whatever that works out to be. $1,728. So that's 1,728 square inches is my area. Well, okay. How much pressure then is against this door? Well, we know inside the aircraft that, let's just say, our differential pressure between the inside of the aircraft and the outside of the aircraft is 5 psi, just to make the math easy. So we're going to say our PSID is 5 psi. So that's a pressure, and we have an area. So what do? We go over here to pressure. Pressure is force per unit area. So we put our 5 psi into our pressure. Force we don't know. We do know an area, which is 1728. So if we do 5 times 1728, that gives us 8640 as a force. What are the units? It's not newtons, because we use pounds per square inch for pressure, and we use square inches for area. But because we're using that same unit base, we know that our force is going to come out in pounds. So this is the amount of force that you need to apply to open that door in flight. 8,640 pounds. Now, I'm a big dude, but I don't think I can lift 8,000 pounds. I bet it would take 10 guys. I mean, even if you had 10 people, that's still 864 pounds a person. They have to exert some force to pull that open. You're not opening that door in flight. There's no way. So this is why anytime you see this on a movie or on a TV show or something, and they're worried about, oh no, somebody tried to open the door in flight. So it's not going to happen. You can unlatch it all you want, but just the pressure is going to keep it there. Now, air in this case is our fluid, right? So if we look at our example of the needle, let's think about what that looks like. Remember, our pressure is force per unit area. Well, we really kind of want to look at the force that we're going to feel, or the pressure that we're going to feel from the needle, right? Well, how much pressure do we need? If I poke you with my finger at, say, 10 newtons of force, and the area of my fingertip, that's going to be something low, right? Maybe 0.005 square meters. So that's gonna be on the order of what, 200? Pressure. So the point is, it's not a whole lot of pressure, right? But what if we take the needle? What's that needle diameter? It's really, really low. Your typical needle is about 0.04 millimeters. So what's 0.04 millimeters in meters? Well, 0.04 millimeters. If we want to convert to meters, we have to move this decimal place to the million, right? So how many millimeters in a meter? 1,000, right? Million. So we have to move the decimal place 3 to the left. So that's 0.00004 meters. If we square this, stick it in our area, you can see that even with just 10 newtons of force, the pressure goes way, way high. That's why the needle can penetrate your skin. If you want another example of this, think about if you're out at the club or at the gym or something, and somebody steps in your hand. Let's say I come along and step on your hand. I'm a big dude. And I step on your hand with my tennis shoes. It's gonna hurt. Don't get me wrong, that's gonna hurt. But you're probably gonna go, ow, and stand up and shake it off. It's gonna feel okay. Now, what happens if I put on a set of high-heeled shoes? Don't think about that too long. But if I put on a set of high-heeled stilettos and I step on your hand with just the heel. So think about the square inches. Think about the area of the bottom of my tennis shoe is way, way bigger than the area of the heel end of a stiletto heel, right? So as that area goes down, if the force remains constant, which is going to be my weight, if the area goes down, the pressure's got to go up. So that means if I step on you with high heels, I might penetrate your hand, right? I might punch all the way through your hand. This is a thing that we had to be careful of working on airplanes. We had hydraulic systems that ran all our flight controls, things like that. Now, remember I told you your typical car tire has an inflation pressure of about 32 pounds per square inch, 32 pounds per square inch. On a typical aircraft, the hydraulic system is pressurized to 3,000 pounds per square inch. So it's 100 times higher than your car tire. If I ever had a leak in a hydraulic line, now if you're lucky, you'll get just a split, you get a fitting come apart and you spray hydraulic fluid everywhere. The more dangerous thing is that if you ever got like a pinhole leak in a hydraulic line, so think about what's going on, think about the force. So pressure is force per unit area. Well, if my pressure is 3,000 PSI, and the area of that pinhole is 0.0004 square inches, you know, something very, very small, then look what happens. That force goes way, way high. This is enough to cut your fingers off and you wouldn't even feel it. So that's why if we ever had hydraulic leaks on the airplane, the way to find them was not take your hand and run it along behind the line to see if you could feel the leak, because you wouldn't feel anything. That was actually very dangerous too, because it turns the hydraulic fluid into a mist, that you can breathe. And breathing hydraulic fluid mist is not good for you. It tends to cause you to die. So, yeah, that is pressure. Let's look at a couple more examples in the slides here. So here's your tire. This is how your tire pressure gauge works. So here's our tire inflated with air. And we have the little valve stem. You know, when you go to put air in your tire, you have to hook up to this little valve stem. So look inside, look at the forces. We have forces against the edge of the valve stem, against the edge of the tire. Obviously, it's not just in these directions, it's everywhere, but we can certainly measure the force against this valve with a spring. Because remember, we looked at springs, we looked at spring kinetic energy. And so we can measure the amount of force it takes to compress spring. Well, if we connect that spring to a gauge, either digital or an analog gauge, like you go buy at the gas station, and you hook it up to that little valve stem, and that thing goes up to 30 PSI or something. That's how we measure tire pressure. And that's how that little valve works. Notice it's two-way. So if you put your air pressure or you put your air line onto the tire, if the pressure in the line is higher than the pressure in the tire, air will flow into the tire until such time that the pressures are equal and that valve will close. Here's just another kind of quick example of what pressure looks like. So let's say we're swimming and we're in some fluid, in this case, water. The pressure is going to be equal everywhere. In other words, you're not going to get a significant pressure difference on the top of the guy versus the bottom of the guy, or the head versus the foot. Yes, there is some minor pressure gradient, but not enough that we're going to have to worry about. So here is kind of the example I was talking about with atmospheric pressure. So our volume, let's say we have this cylinder. The volume of this cylinder is just the area times the height. This is just basic geometry. And here's our force, which is just the weight, just mass times gravity. We use this in engineering a lot. So if we want to know how strong to build a dam, for example. So here's a dam, and here's some water. We know the force behind this has got to be pressure times area, right? That's just rearranging. Pressure is force per unit area. So force has got to be pressure times area. But remember, pressure, what's pressure? Pressure is going to be a function of how deep you are. So how much stuff there is. So that's our H. Our rho, remember, is our density. So density of water. And then A, rho GA, or sorry, rho HA. A in this case is G, acceleration due to gravity. So if we know our pressure is the height or the depth underneath this thing times density of the water times gravity. So here I know how much force is exerted against this dam wall at this depth. Well, if I now know how long the thing is, I know how much total force I'm pushing against, right? And that tells me how big I need to make the dam. So how do I know that? I'm going to go to a materials engineer or civil engineer, and I'm going to say, if I want to make this dam out of concrete, how big does it have to be? What's the density have to be in order to withstand X amount of pressure? And that's going to be a function of the material properties of concrete, which is things like density and porousness and stress strain, something called Young's modulus. If you care about that kind of stuff, take a mechanical engineering class. Really interesting, but useful. Come on. So here's our atmospheric pressure. So if we have a square meter, our weight of the atmosphere is 1.01 times 10 to the 5th newtons. So if you work this out and you find the pressure, we generally talk about pressure in terms of pounds per square inch. Generally, what you'll find here is if it's force per unit area and we use SI units, we get newtons per square meters. The Newton per square meter is called a Pascal. That is the SI unit for pressure. It's pascals. So capital P, lowercase a. Be very careful in homework assignments and test questions. If I give you pressure problems, be very careful to understand what units you're dealing with. You may need to convert from pounds to newtons or from PSI to pascals or back and forth, or I may give you what you need, right? You need to develop this sense of what units am I looking for and what units am I given? Know what you're working with. If I give you imperial units and I ask for a unit in SI, an answer in SI units, then you probably should convert. If I give you SI units and ask you for an answer in SI units, then you really don't have to do any conversion, right? But just know the difference. This is why on week 1, I spent a lot of time beating you up about unit conversion, because now we're going to need it, right? This is an example of using the concept of equilibrium and pressure together to do work. Remember what work was? Work is force times distance, right? Well, we know that pressure and force are very closely related. So in this example, here's what we have. We have a couple of pistons. Piston 1 and piston 2. Piece of 1, piece of 2. We apply some force on piston 1. Notice we apply that force down. Now, below this piston is some fluid. I don't know if it's water, or hydraulic fluid, or grape jelly. It doesn't really matter. And they're connected. The surface area of the two pistons is different. So what we can do here, because these two systems are connected, that means they're going to try to maintain an equilibrium, right? And because force has got to be distributed equally, what we can do is we can find out our force per unit area on the left side. That's going to be our pressure, right? So if our force is given and our area is given, then we know our force per unit area or pressure here has got to be equal to the pressure on the right side. But since the pressure on the right side is also force per unit area, and we know this thing has a new area, different area, then what we can do is find the resultant force. A typical application of this is a hydraulic lift in a car shop. So if you go in to, say, have your oil changed, well, now they generally have you drive over this thing, it's a pit, and the guy gets down to the pit and does it. But sometimes you will still see you drive into the garage and they put you on a lift and they raise you up. Now, the way they do this, if you've ever watched this, is usually the way they lift the car up is they go push a button. And that button turns on a motor, turns on a pump, and the car goes up. You might also see this manually. You can buy a truck jack down at AutoZone. You stick it under the car, you pump a handle, and the car goes up. Well, notice that when you're doing that, you're not exerting a whole lot of force. Not putting a whole lot of effort into it, but you're able to lift this 2,000-pound car. Well, that's because of this principle here. It's because of that difference in pressure, but the system wants to maintain equilibrium. So if you have a small enough surface area and you apply force, you get more force out. So you're doing work. How much work are you doing? Well, it depends on how high you lift the thing, right? Because work is force times distance. You see why I don't really give a comprehensive final in this class? Because everything that we do all semester long builds on itself. We've been doing comprehensive stuff all semester. This is kind of where you start to recognize that a little more, I think. But we've already been doing comprehensive exams all semester. So I see no reason to punish you and torture you by making you go back and redo the same thing, especially when the majority of you are not physics majors. Now, you guys that would, if you were a physics major in my calculus-based class, you might be having a bad time right now. This is a little more complex example using that Pascal's principle. This is how the brakes in your car work typically. I'm not going to go into this in depth, but you can go look at it and see that it's just a mechanical system. It's about applying a force to generate a pressure to do some work somewhere else. This is why we went over all that stuff about statics. And remember, the title of this section is fluid statics, right? So that's what we're doing. This is what I was talking about, using a spring to measure forces. So if we have pressure on the right side, we have some area that the pressure is exerted over that generates a force. Well, we know a force, we know the length of a pivot arm, so here's some torque, and we know the spring tension and the spring, because we might know a spring constant and the distance the spring compresses. Then it's pretty easy to build a scale to tell us how much pressure this is. It's called an aneroid gauge, by the way. This is how a barometer works, especially around here. On the occasion that we do have tornadoes or something, you might hear the guy on the weather and he'll talk about how, oh, the pressure's dropping. Well, that's what we're doing here. This is how we measure it. You'll hear atmospheric pressure, 14.7 psi, for example. You might hear him say, oh, the pressure is down to 13 psi. So lower pressure. So how do we measure that? The way we typically do that is with something called a fluid barometer or a manometer, if you use water. So what you do is you have this kind of U-shaped tube, you put water into it up to a certain level, and you let both sides be open to the atmosphere. Well, as soon as you close one side and you change the pressure, you're going to cause the level of this fluid to change by H. And if we know the density of the fluid and the acceleration due to gravity, if we measure the height, then we can find out what that pressure is. This is why sometimes in a weather report, you will not hear PSI. You will not hear atmospheric pressure of 14.7 PSI. You might hear something like inches of mercury. Might hear something like inches of water. That's a different way of measuring pressure. So inches of mercury is something we typically use. So why do we typically use mercury in these things to measure pressure? Because mercury is very, very dense. And so we don't need a whole lot of volume. Water is not very dense. So if we try to measure water, try to use water to measure pressure, then you would need to measure the change in feet. And it gets pretty nasty to do that. So you'd need this big instrument. So that's typically why we use mercury. This is also the same principle that a mercury thermometer works on. You've ever seen an old mercury thermometer when you're sick, or you mount one outside, you get this red fluid, or it might be silver, depending on if they dyed it or not. It's enclosed in a tube. That tube has a known pressure inside it. As that liquid gets hot, it wants to expand. And since it's an enclosed tube and it tries to expand, that means it has to increase the pressure, which means the level of that fluid must change. And those things are calibrated to say, oh, a change of 2 millimeters is 1.5 degrees or something, whatever it's calibrated to. So that's how those thermometers work, is on exactly this principle, except we're not using mechanical means to increase the pressure. We're doing with thermal energy. But you should understand enough about physics at this point that we're just talking about energy transfer, right? We're talking about doing work. And as we learned before, energy comes in a lot of different forms. It might be sound energy, it might be light, it might be heat, it might be pressure, it might be some kind of mechanical force, but it doesn't matter. Because all we're doing is measuring forces and balancing forces. Blood pressure measurement does the same thing. She's 82nd Airborne, so I'm not entirely certain she knows how to use that instrument. There's your another mercury barometer, different examples of pressure. Screened area stuff again. Yeah. Oh, hydrometers, these are interesting. Hydrometers measure what's called specific gravity, which is related to density. The thing that you'll see these used in a lot, if you get into the hobby of beer or winemaking, you will use hydrometers a lot. I do a lot of homebrew beer making myself. And so what you do with this is it is a way to measure the density of a fluid. You have some weight in the bottom of the sealed tube and you set it into your vat of fluid and you measure where the line of the water is. And that's going to tell you what's called the specific gravity. The lower the density gets, the higher up this thing's going to float. And so that's, without going into a lot of detail, that's how you measure the alcohol content, because alcohol is much less dense than water. So you take your beer ingredients with all the sugars, you pitch the yeast, let the yeast start eating the sugars. That turns into carbon dioxide, the gas, which is low density, and alcohol, which is lower density than water. So you measure the density of effectively the sugar fluid prior to throwing the yeast, and you wait a few weeks and you come back and you measure that specific gravity again. There's a change in density there. That's what your specific gravity tells you. You throw in this little formula and that tells you what your alcohol by volume is. It tells you if you've made a 3% day drinking beer, or if you've made a 15% wake up in your backyard Monday morning wondering what happened beer. So that is where I'm going to stop for today. I will continue this discussion Wednesday, probably working a few more examples. Again, this was intended to kind of give you an overview and an idea of what's going on. I'll do a few more examples, and probably Friday, I think I will do the magic trick. I'm going to show you how to use fluid dynamics along with conservation of energy to explain why airplanes fly and the concept of lift. It's a pretty cool little magic trick that I do every year, and it's a really fun lecture. So That's where we're going to stop today. We'll continue our discussion of fluids, pressures, that kind of thing. As always, if you have problems, reach out to me. I have posted these notes on Blackboard, and either today or tomorrow, I will post the next homework set along with its due date. So I will see you guys then.